Good afternoon. I'm Moisés Villegas Vallecillos, and I'm going to talk about norm-attaining block mappings on the complex unit disk. First of all, I'd like to thank the organizers, my friends Paco, Fernando and Kenya, for inviting me to this conference. This talk is the result of a collaboration with my colleague Professor Antonio Jiménez Vargas. The celebrated Bishop-Phelps Theorem ensures that the set of all norm-attaining functionals on a Banach space S is norm-dense in its dual space S star. In other words, we can approximate every bounded linear functional by norm-attaining functionals. This interesting theorem has many extensions. For example, an important extension of the Bishop-Phelps theorem was done by Lindström. Lindström proved that the set of all bounded linear operators whose second adjoint attain its norm is dense in the space of all bounded linear operators. In nonlinear settings, the Bishop-Phelps theorem has been extended too. For example, for polynomials, we have these studies of Choi and Kim and Aaron Garcia and Maestre. For holomorphic mappings, we find these researches of Acosta, Alaminos, Garcia and Maestre, and Carando and Mazzitelli. More recently, the Bishop-Phelps theorem was extended for lattice homeomorphisms by Dantas, Martínez-Cervantes, Rodríguez-Avellán and Rueda-Zoca. For Lipschitz spaces, we have extensions of the Bishop-Phelps theorem due to Godefroy, Cadets, Martín and Soloviova, Cascales-Chiclana, García-Lirola, Martín and Rueda-Zoca, and Choi and Martín. For example, Cadets, Martín and Soloviova proved that the subset of attaining Lipschitz functions in the pointed Lipschitz space, Lip subset of ESC, is weakly dense in this space, in the pointed Lipschitz space. Compare with Bishop-Phelps theorem. Here we have the pointed Lipschitz space instead of the dual space X star, and we have weakly density instead of density, but the pointed Lipschitz space is bigger than the dual space X star. We want to study this type of problems about norm-attaining functions on the normalized block space, the space of block functions on the complex open unit disk. Next, we present the normalized block space, its pre-dual, and we study the strand points of the unit wall of this pre-dual. Let's set some notations and definitions. D will be the open unit disk in the complex plane. ESC will denote a Banach space, and B hat of the ESC will denote the space of all holomorphic functions f from D to ESC vanishing at 0, such that this set is bounded. Broadly speaking, that means that there is some control of the derivative at the boundary of the disk. Then we can consider the supremum of this set, P sub B of f, and it is a norm on the space B hat of the ESC. The space B hat of the ESC with this norm is a Banach space called the normalized block space. An important subspace of the normalized block space is the normalized little block space, B sub 0 hat of the ESC. It is formed by all functions f in the normalized block space such that this limit is equal to 0. To simplify, when ESC is the field of complex number, we use these symbols to represent the corresponding normalized block spaces. We can find a study of block functions in this monograph of Su. A very useful example of a little block function is the following. Given a point z in the open unit disk, the function f sub z is defined in this way. Then f sub z belongs to the little block space. Its norm is equal to 1, and we have this equality and this inequality. Observe that the equality is only true for Z, because if W is different of Z, then this is less than 1. In general, when this expression coincides with the norm of the function, then we will say that the function strongly attains its block norm. In this example, the function f sub z strongly attains its block norm only at the point z. On the other hand, we will use the following functionals called block atoms. They are evaluations at the derivative. And to have a norm 1 functional, we multiply by the inverse of the norm of the functional of the block atom, of the functional gamma subset. We denote by gamma sub Z hat the normalized block atom. Finally, the closed linear hull of the set of block atoms is called the block-free space, the block-free Banach space. And it is denoted by G of D. Antonio Jiménez Vargas and his student David Ruiz Casternado show that the block-free space G of D is separable and it is the predual of the block space B hat of D via the evaluation mapping. Then we have in the normalized block space a weak star topology, and taking into account this topology, the normalized little block subspace is dense in the whole normalized block space. Is closed in norm but dense with the weak star topology. Moreover, G of D is the dual of the normalized little block space via the restriction mapping. The extreme points of the unit ball of the normalized block space and the normalized little block space were studied by Zimma and Wogen. Our first goal is to determine the extreme points of the unit ball of the block-free Banach space G of D. To do this, we embed the normalized little block space into the space C sub 0 of D of all complex continuous functions on the open unit disk vanishing at infinity via this mapping phi sub 0. We consider this space C sub 0 of D because we know that the set of extreme points of the unit ball of the dual C sub 0 of D is this set, the set of evaluation functionals multiplied by unimodular complex number. Moreover, we can consider the adjoint operator phi sub 0 star defined between the duals of these spaces. From the following general and interesting lemma about extreme points due to Kulkarni and Limaye, we can prove that the adjoint map, the adjoint operator phi sub 0 star is a surjective mapping between the sets of extreme points of the corresponding balls. using the mapping phi sub 0 star between the sets of string points, we can obtain that every string point of the unit ball of the block-free Banach space is a normalized block atom multiplied by a unimodular complex number. And the reciprocal is true too. And this is our first theorem. Now we are going to see our main result. First, remember that a bounded linear operator T between two Banach spaces x and y attains its norm at the points x of the unit sphere if the norm of T of x is equal to the norm of the operator T. We introduced some block variants of the concept of norm-attaining operator, taking into account the following result of Antonio Jimenez and David Ruiz. For every block function f, there exists a unique bounded linear operator S of f from the block-free Banach space G of D into the space S, such that this diagram commutes. Furthermore, the norm of the operator S of f is equal to the norm of the function f. As a consequence, we can identify the normalized block space with this space of bounded linear operators. Then we say that a block function f strongly attains its block norm at a point z of the open unit disk if this expression reaches the maximum value at z. This is the natural definition of attaining the block norm, but we can give another definition taking into account the previous result. We say that a block function f attains its block norm at a functional gamma of the block-free Banach space if its linearization S of f, the operator S of f, attains its operator norm at the functional gamma. It is easy to see that every block function strongly attaining its block norm attains its block norm, that is, verifies the second definition. Concretely, if f strongly attains its block norm at the point z, then f attains its block norm on G of D at the normalized block atom gamma hat sub z, that is, S sub f attains its operator norm at this functional. And reciprocally, if S of f attains its operator norm at the functional gamma hat sub z, then f strongly attains its block norm at z. But what happens if S of f attains its norm at another functional, gamma. Does f also strongly attain its block norm? Surprisingly, the answer is yes. The set of norm-attaining block functions coincides with the set of strongly norm-attaining block functions. And this is our second result. Here we have some ideas of the proof, but we skip them for the sake of brevity. Finally, we present our main theorem. The set of block functions strongly attaining its block norm is norm-dense in the whole normalized block space. We comment some ideas of the proof. In the scalar valued case, our previous theorem with the Bishop-Phelps Theorem and the linearization theorem of Antonio and David give the result. In the general case, we replace Bishop-Phelps theorem by this theorem of Bourgain about strongly exposing operators. And reasoning in the same way, we obtain the result. We obtain our main result. To finish, we present some consequence for compact block functions. If f is a block function, this set, the block range of f, is bounded. Motivated by this fact, we say that f is compact block if the block range of f is a relatively compact subset of S. We denote in this way the subset of the normalized block space formed by all compact block functions. Antonio and David proved that the linearization identification is an isometric isomorphism between the space of compact block functions and the space of compact operators between the block-free Banach space G of D and the space X. Taking into account this result and the previous Bourgain's theorem, we can obtain a result similar to the main theorem for compact block functions strongly attain their block norms. The set of compact block functions that strongly attains its block norm is norm dense in the whole space of compact block functions. These are the references And that's all. Thank you very much for your attention.